We now go on to modeling. Instead of building a model from scratch, we're gonna apply transfer learning. That is a model which has previously been trained on a huge data set, like say the COCO data set or Pascal VOC data set, can now be fine-tuned on this custom data set, which involve the ripe and the unripe fruit. We also have the error sanctioning, training optimization, and performance measurement. In this case, we're going to be using a YOLO model. So the error or the loss function we'll be using is a YOLO loss, which is defined in the YOLO paper. Then we shall train the model, and then the performance metric commonly used in this is the mean average precision. Then we have validation and testing. So we're going to split our data set into two parts, the training and the validation set. And finally, we have some corrective measures to better our model performance. Clearly, one of the most important corrective measures we could take is that of increasing the data set, and we've spoken of that already. So in case you want to put this kind of system into production, you need to get as much data or as much representative data as possible. Now, another good news is for this parts, we would not need to write out the code from scratch. We are going to make use of this existing code base by Zihao Zhang, which makes use of the original pre-trained darknet weights. Now, darknet is the model which is used in the YOLO version 3 paper. So first thing, you could go ahead and clone this repository. There we go. We have some key features, and here are some examples. There we go. You start by installing, so you should have TensorFlow installed. You could check on our video which explains how to install TensorFlow, both CPU and for GPU. Now, after installing the TensorFlow GPU, you would also need to install OpenCV Python, LXML, and TQRDM. While LXML is used for handling XML files, for example, the kind of annotations we're working with, the TQRDM is used for showing progression as we train a model. In the case you're using a GPU, which is advisable, you will need to install the drivers, and then you go ahead and convert the pre-trained darknet weights into TensorFlow weights. Before conversion, we need to first download the weights by using this command, or just simply copying this and download it directly on the browser. So we could copy this, and there we go, it's downloading. After downloading, we have it in this data folder. There we go. We now go on to do the conversion. We have this command right here, Python convert. That's the weights we just downloaded. There's it here, and then we output it as the TensorFlow weights. Now, since we're working with the YOLO version 3 and not the YOLO version 3 tiny model, we're gonna copy this instead. So we have this right here, copy that, and then paste. So there we go. Now this is going to convert this from this data folder into the checkpoints folder. The convert.py file isn't found in this directory, so we need to change directory. There we go. We now put back that command, and that's it. The weights have been saved, and get into the checkpoints folder. This is what we get. From this, we could go on to detection, so we could test this pre-trained model actually. And to do this, we just have this command right here. So we could again copy this, paste it out right here. Let's modify this. Let's take the street.jpg, this image right here. So that's fine. Run this. There we go. In the command, we already see the different detections, and this has been saved into this output.jpg file right here. And this is it. Yeah, the results we get from this detection. But let's now try with the strawberry images we have from our data set. Yeah, we have this. Instead of this, we're gonna have this actually a strawberry image, or an image that was drawn from our custom data set. Let's run that. And as you could see, unlike the previous output where we had the detections, here we have actually no detection. So this is normal because this pre-trained weights were gotten from training on the Cocoa data set, which doesn't have this kind of images, or which is made of images which don't have the strawberry as an object. So the Cocoa data set doesn't take into consideration a strawberry as an object. So the model doesn't learn how to detect and classify strawberries. So in that sense, we are now going to do a custom training based on the data set we have at hand. Under the docs, we have this training VOC file right here where you have the training instruction for our custom data set. In this example, the author actually is considering the Pascal VOC 2012 data set to be the custom data set, though ours is different, but we shall follow the instructions given in this file right here. So firstly, they start by downloading the data set. This is the data set we've created already, so we can skip this step. We move on to transforming the data set. You see here, they specify the directory to the training set, and then we have this output TensorFlow record file which is generated. Now the reason why it's preferable to work with the TensorFlow record is because it's an efficient way of storing data. And apart from that, this TensorFlow records, or many TensorFlow records, could be created from a very large data set. And if we could break this large data set into several TensorFlow records, it means we don't have to always load the full data set in memory before training. So that's why this TensorFlow records are highly used in this kind of applications when doing training. One thing we've done with the data is that we've broken it up into two parts. That's the training and the validation. So with the training, we have 527 items, and then with the validation, we have 86 items or 85 items. So it's a 87-13 split. That is 87% of the full data set is for the training, and then 13% is for validation. So there we go. We have the Python tools, the data directory, the split is train, output file, here is it. Now we've modified it from VOC 2012 to strawberry. So that's it, we'll run that. And we have this error where we're told that there's no such file as this. Now the reason why we're having this is because in here by default this classes is set to the VOC 2012 names. And since we have it instead the strawberry.names, we need to set this classes to strawberry.names. And that's just what we do. We modify this. So now we have those classes, and then we have strawberry, the names, we have data, and that's it. So we have that. We run again. But this time around we have this other error telling us that there is no such file or directory. This file doesn't exist with this train.txt. And that's true because in this main we have the two files, that's ripe.txt and unripe.txt. So let's modify that. Here the way that was set was such that in this, based on the split, that's based on whether the split is a train or validation, we're gonna have here train.txt, and when it's validation we're gonna have val.txt. But that's not how we prepared our data, so we could simply take this off and then set this to ripe. So we have that. Run this again. Now we get this other error right here. To solve this, we just simply have to take off this here. So we'll take this off, run again. This should be fine now. This time around the image list has been loaded, but unfortunately there's this error, key error, difficult, which was not found. And the simple reason why we're having this problem is because in the way we're creating this data set, the XML files we created didn't have the difficult tag, the truncated tag, and also the views tag. So let's simply take that off. We'll take this off, take this truncated views. Down here we take this off too. So we take that off. And there we go. So let's go back to the command and retest again. Back to the command, run that again. We've now loaded or created the TensorFlow record for the trained data. We can now go ahead to do the same for the validation data. So right here, we just have that. And then we modify this. So here, instead of strawberry, we say strawberry val. So we have strawberry val. The split is validation. So we have val. In here, we have validation. So that's it. We run again. We see now that instead of 527 images, now we'll have just 85. So we load that quickly, and that's fine. And here are the two files in question, the strawberry and the strawberry val. We now move on to the training, where we'll specify the data set for both the training and the validation, which we've created already. Here we have the strawberry TF record and then the strawberry val TF record. We have the classes. Here we have strawberry.names. Number of classes in this case is 2. The mode is fit. We're doing transfer learning based on the darknet model, which has been trained on the Cocoa data set. Batch size 16, number of epochs 10, which you could also modify depending on your particular problem. So in a case where your model isn't overfitting, you could continue training to get the best out of it. Though in this implementation of the YOLO version 3, the L is stopping, so that in a case where the validation loss doesn't increase, then training could be stopped. You also have to specify the weights. Yeah, the weights we had converted previously. That's from this initial weights to the TensorFlow type weights, and then we specify the weight number of classes. Now these weights come with an initial number of classes, or they were trained on the Cocoa data set with 80 classes. In this case, we don't have that exact number, so that's why the number of classes here is different from the number of all the weights number of classes, or the initial number of classes. Now supposing you have trained on the strawberry data set with just 2 classes, and then you want to retrain based or using the weights from the training on the strawberry data set, then in that case you would have to specify a different checkpoint right here, and then the weights number of classes will be 2 instead of 80. That said, let's get into the code. So we have this, we specified all this. Strawberry TF record for the validation, classes, number of classes, the mode, the byte size, number of epochs, and that's fine. So we could run that. Here's the training process. We train about the 10 epochs. We have the YOLO loss that's dropping from 2600 to about 44, and then the validation loss right here, which drops from 3500 to 50. So from this we see that we could continue training since the model isn't overfitting. But for now we shall go straight away into detection, and that's it. We have the Python detect.py, specify the classes, number of classes, weights, and then the image. The author also specifies that in the case where we haven't trained for long, we may need to lower the object next call. We put that in here. We have detect, specify the classes, number of classes, the weights. Here we have image, so here's image instead. Take that off, and then we specify the image we want to run inference on. Recall that this was the same image we had done or run inference on previously, which had no detected object. So let's run this again now. As you could see from here, we have no detections. And since we didn't train for long, we are going to reduce this score threshold right here. So we'll go from 0.5 to 0.1. Save that. Run this again. And there we go. We now have some detections, which we shall see in the output.jpg file. Opening up the file, this is what we get. So right here, we have these detections. Now what we could do is continue training our model. So we'll just keep training now for 30 more epochs. After training for several epochs, here are the results we get. We'll see how we go from the first epoch to the 11th and up to this. You see how the validation loss keeps decreasing right here. So we could continue with the training since the model isn't overfitting. We have that. There we go, up to this point where we observe some convergence of the model. Now note that at around this point, the training loss will continue reducing, but this doesn't mean we have to continue with training, since if the validation loss doesn't reduce or if the validation loss starts increasing, it simply means your model is overfitting on the training set, and so you have to stop training. Nonetheless, early stopping was implemented, so you shouldn't have to bother about that. We now go straight away into testing. We use the same image we had tested previously. We have that. Notice how we're using the model weights after the 25th epoch right here. There we go. Here are the results we obtained. Now if we check on this output, that's what we have. So we see that the model performs perfectly well, as it's now able to correctly detect all the ripe fruits. Here are some other examples which were detected by the same model. See this one right here. We have this miss here, and we also have, no, that's fine. Yeah, this is unripe, so it detects this as an unripe fruit. We have this other one. See that it gets this ripe correct, ripe, unripe, but it doesn't get this other detections correctly. Note that the poor performance of the model on this type of image is also due to the fact that we don't have any of this kind of image in our data set. So since we're taking this from a completely different distribution, the model hasn't learned well how to do detections when faced with this kind of images. We now go to the next. We have this other one right here. You see that this correctly classifies this as unripe and yeah, ripe. You see also the scores, like this is 0.39, so it means if we had decided to pick a threshold of 0.5, then this wouldn't have been detected. So depending on your problem, you have to choose the right threshold. So don't save. We have that. Next one, you see this isn't even a strawberry, and there is no image of an apple in our data set, but the model successfully detects this apple. Although the bounding box isn't perfect, it does a great job in detecting that there is an apple in this image. Next, final one, see it detects this an unripe, ripe. It doesn't see this. So that's it. You've just seen how to prepare your data, how to train the model, and how to do detections like this. Now we move on to some corrective measures. The very first one is to collect more data. In this project, we used around 612 data points with 527 used for training, which is very small if you have to deploy a model in production. So in case you want your model to perform better, you just have to collect much more data. And then the second problem is, in this our data set, we have way many levels of ripe strawberries compared to the unripe ones. And this kind of data set is known as an imbalanced data set. So what you have to do is to try to balance the data set. And to balance the data set, it means you could gather much more data in which there are unripe strawberries, such that the model learns better how to detect the unripe strawberries. You would have noticed in the different examples that, or the different detections, that the model was struggling to detect the unripe strawberries as compared to detecting the ripe strawberries. And this is simply due to the fact that the data set was imbalanced. Another way in which we could solve this problem of the imbalanced data set is by introducing some regularization in the computation of the loss. That is, penalizing even more the model when it makes an error in correctly classifying and detecting the position of an unripe strawberry as compared to that of a ripe strawberry. So there we go. We've learned how to prepare our own custom data set and also train it to detect the ripe and the unripe fruits. For this week's giveaway, what you'll do is train on your own custom data, then choose one of those courses, say for example this one, and then apply for a scholarship. In your application, make sure to include a sample output from your object detection project. In this course, we'll treat the YOLO version 1 and YOLO version 3 models from scratch, so you get to understand exactly what's going on under the hoods. Hope you enjoyed this video. See you next time.